the trapezoidal rule. We saw about estimating using rectangles, and it wasn't great. Just to make it a little bit better, instead of using a rectangle, if we use a trapezium, straight away we've cut out some of that overestimate. I suppose it depends whether the curve's concave up or concave down. See, because that one's concave up, so a trapezium would create an overestimate. If the curve was concave down, so imagine it being concave down, drawing the same picture, you'd end up with an underestimate. So we're going to estimate it with a trapezium. I hope, remember the formula for a trapezium. Half the height of the trapezium, in this case that would be b minus a, sum of the parallel sides. So function a plus function b, whatever that is. Okay, but as we saw with rectangles, if we increase the number, the better the estimate. So let's put another one in the middle there, call it c, and we try with two trapeziums, hence why it's called the trapezoidal rule. Because I don't know if you know this or not, but in America they don't call it a trapezium. They actually call it a trapezoid. So the area then of our two trapeziums would be, well, what I've written down there. But you've got c minus a and b minus c. So if you're smart, you pick c such that it's in the middle. Then that way, b minus c is the same as c minus a. And we can factorise this formula then. So we'll use c minus a because we're saying they're the same thing. But we'd end up with a function a, a function b, but function c would be in there twice. Let's split it up into three. So now we've got a c and a d. And we can see from our beautifully drawn picture there that, wow, that overestimate is now getting very small. There's our formula, but once again, if we choose c and d clever, so that all three of those are the same, I can factorise that into one thing. Let's call it c minus a. And we see a pattern emerging. We're always going to get function A and function B, but we'll get twice all the ones in the middle. Makes sense, because the ones in the middle are involved in two different trapeziums. So we could generalise this formula and say, look, we know it's going to be exactly that. But let's say we've got a function that we can't integrate, and there are some functions that, quite frankly, we just can't integrate. We don't know how to do it. So we've got to have some sort of estimate. So if we were to use our trapezoidal rule, this is the way I write it down because I can't think of any other way of writing it. So I say h on 2, so that's the height of the trapezium. Y naught, I call the first one y naught rather than y1 because if you notice it, there's always one more than the number of trapeziums that you're using. See how there's 4 different values there, A, B, C, D, but 3 trapeziums. So if I start at y naught, then the last one will always be y whatever the number of trapeziums we're using are. And then what do I say for the ones in the middle? I say, well, just 2yr, the others. Okay. Where, yes, our height will always be, it'll be b minus a, but we've split it up into n trapeziums. We've done it evenly so they're the same, so we'll divide it by n. So as I say, note, remember there's always going to be one more function value than there are the number of intervals that you draw. That brings me up to another thing about terminology. Sometimes they'll say trapeziums, make it nice and easy. Sometimes they'll say intervals. Sometimes I've seen them use the word strips. Sub-intervals I've seen them use. What else is there? Yeah, I mean, you just got to get used to the different language that they might use. Hopefully it'll be obvious. It should be obvious. Most commonly they'll say intervals, I think. Such as this one. We're going to use the trapezoidal rule with 4 intervals to estimate the area under this one here. I purposely did this one because we can work out the exact value. I hope you recognise what the curve is. 4 minus x squared to the power of half is, of course, semicircle. But we're going from 0 to 2, so it'll actually be a quarter of a circle, radius 2. So we know that's what it should be. But let's pretend we don't. Okay, let's work out our height. B minus A, well, we're going from 2 to 0, and we're going to use 4 intervals, so that's 2 minus 0, 4. They're going to be a half. I then draw myself up a table of values. Say, righto, these are the different x values that I'm going to use. Go to my calculator. They've said 3 decimal places. So that's why I've done 4, just in case there's a rounding error. So I'll take it to 3 decimal places in the last step. There's my formula. Wow, I suppose you don't have to write the formula down, but there it is. H on 2, y naught plus 2y others plus yn. Then I always do this just to make sure I don't make a mistake. I know the end ones are times 1 and the middle ones are times 2. So I always just write that above it on my table of values. 1, 2 for all the other ones. So then we just sub it into our formula and calculate it. So there it is, 2.996. So what is a quarter circle? Pi actually. Works out to be pi, which we know is about 3.14. That's not too bad. Percentage error. So to 3 decimal places, pi is 3.142. So we've got about a 4.6% mistake on that one. It's okay. Alternative way of working out. I found this a few years ago now and went, wow, that's different. That's not too bad. See what you reckon. There's our table of values. So to get the answer, now look at the answer very carefully. It still has the 1 times the end ones and the 2 times all the middle ones. But notice on the bottom of the fraction, it's the numbers that I've written on the top of the box, but we're just adding them together. 1 plus 2 plus 2 plus 2 plus 1. And then you just multiply by b minus a. And amazingly, I guess you're just going to have to trust me. Oh, look, it's the same thing. But it works out. Here's one from a couple of years ago. So 2020 HSC, question 20. Kenzo is driving his car along a road while his friend records the velocity of the car, kilometers per hour every minute over a 5-minute period. And then we got velocity time in a nice table there. They've told us that the distance covered is equal to this integral. Use the trapezoidal rule and the velocity at each of the 6 time values to approximate the distance done. In other words, it's just a really fancy way of saying solve this integral using the trapezoidal rule. But they just put lots of words in there to confuse people. Okay, there's my table of values. Trapezoidal rule they want. H on 2, y naught yn, 2y the others. So 1 times the m ones, 2 times all the ones in the middle. Sub in, bang, there's our answer. 5.4 kilometres. So it's not too hard. It's just, you've got to remember 1, 2 times the ones in the middle. Of course, if I did it the other way, so same sort of thing, but the end ones minus each other. If you use that setting out, there you go. Okay, so that's our trapezoidal rule.